This video walks you through the example in Chapter 5 of the text, specifically talking about a single sample t, effect size, and confidence intervals. This video applies the 4 pillars of scientific reasoning to a research example comparing one sample mean to a value of theoretical interest. In other words, an example when we would use a single sample t-test. This is the first chapter where we truly apply all 4 pillars of scientific reasoning to support a scientific conclusion. The graphic here again describes what we're trying to do. We want to hold up a scientific conclusion with both scientific evidence and the scientific context. We think about these things as 4 distinct pillars: hypothesis testing with a continuous p-value, talking about the practical importance with effect sizes, estimating the population parameters with confidence intervals, and then interpreting all of that statistical evidence based on the strengths and weaknesses of the methodology and comparing the results that they provide to the results that are reported by other scientists in the scientific literature. By doing all of that, you're going to be able to develop a well-supported scientific conclusion. The research question we're trying to answer with this study is, do psychology majors overestimate the starting wage for their first job? Now, if you read the literature on optimism bias, you would be able to form a scientific hypothesis or an expectation or prediction that's based on that literature. And if you had done that in this case of optimism bias again, you would expect that psychology majors, like a lot of other students and a lot of people in general, tend to be overly optimistic. In this case, we're specifically measuring starting wages. Now, in addition to your scientific hypothesis, you also have to be aware of your statistical null hypothesis. Your statistical null hypothesis is important because that's the basis on which we will be able to form statistical evidence. The statistical null hypothesis is the statistical outcome that you expect if there were no effect in the data. So in this case, it would be the effect that you would expect if participants are not overly optimistic, if they were just accurate at predicting their starting wage. And in this case, the value of interest we're going to use is a value that was obtained from research that found that the actual starting wage for psychology majors when this data was collected several years ago was $18.75 an hour. So that's going to be our test value. That's what we're going to compare the sample mean estimates for starting wages to. And again, the statistical null hypothesis would be that the sample mean will be equal to $18.75 if participants are accurate. One of the important decisions you have to make when you're conducting your own research is determining the sample size that you're going to need. Generally, larger sample sizes are better because they have less sampling error. They have a better ability to detect statistical evidence. And that's another way of saying they have more statistical power. It's going to take more participants to detect a smaller effect, and it's going to take fewer participants to detect a larger effect. In this specific example, the previous research, if you read it, would indicate to you that you would expect a large effect for overconfidence here. So you would be able to get by with a smaller sample size of, say, approximately 25 people per condition, because you have a D that is, you're expecting a D that is a large effect. The first thing we're going to do now is start walking through the statistical pillars. And the first statistical pillar is hypothesis testing with a continuous p-value. And the first step for that pillar is to choose the correct test statistic. In this case, you are comparing a sample mean to a population mean, and you do not know the population standard deviation. In a situation like that, you want to use a single sample t. Specifically in this scenario, we are comparing psychology majors' estimated starting wage, which is a sample mean. So we're going to collect a sample of people. We're going to sample of psychology majors. We're going to ask them what they anticipate their expected starting wage will be. We're going to compute their mean, and then we're going to compare that to the actual starting wage of psychology majors for this population. And that would be mu. The second step is to evaluate or examine the statistical assumptions. The single sample t has 4 statistical assumptions. The first one is data independence. And that simply means that the participants' responses to your question about what their expected salary might be, one person's response is not influenced by another person's response. So a poor example of how to collect this data would be go to a group of people in a classroom maybe and ask the first person, what do you think you're going to make your first job? And then they would report out loud, and then other people would hear it. Perhaps other people hearing that person's response would cause them to change their estimates. And so that would violate the assumption of data independence. You just want to make sure that each person's response is independent of another person's response. The second assumption is appropriate measurement of variables. When you're talking about a single sample t, that means that the independent variable is going to be nominal. In this case, it's going to define how the one group or the one condition, the sample, is different from the population. In this case, the sample is providing an estimate of what they think their salary will be, and we're going to compare that to the population, which is not an estimate, but the actual value of their wage. So again, the independent variable is nominal, and it's saying how the sample group is different from the population. In this case, they're providing an estimate of their wage, and we're going to compare that to the population mean of their actual wage. The dependent variable is always going to be measured on an interval or ratio scale of measurement when you're doing a single sample t. The normality of sampling distributions assumption relates back to the central limit theorem that we talked about previously. The population of estimated salaries should have a normal shape. And there is good reason to believe that it would have a normal shape in this case. The other way that we can satisfy this assumption is if the sample size that we're using is sufficiently large. In this case, we're going to be using a sample size of 25 because we want to try and detect a large effect. So it's probably pretty close to satisfying that, but we also have good reason to believe that the distribution of sample means for the estimated wages will have a normal shape simply because the population does have a normal shape. So it will have because the population does. The final assumption is the homogeneity of variance assumption. And this is that the sample standard deviation is going to be similar to the population standard deviation. Now this is hard to check because, again, we don't know the population standard deviation. So this is just an assumption, and we really have no way of verifying it. The third step is to formally identify the statistical null hypothesis. So again, the null hypothesis is always based on the idea that there is no effect. So in this case, if there is no effect of over optimism or overestimation of wage, if there is no effect, you would expect the population's mean wage estimate to be exactly $18.75 an hour. That's what you'd expect if there is no overestimation going on. There's no effect. There's no optimism bias. Formally, you would write that as the mu is equal to 1875. Now, if you get a mu of 1875, that means that you would get a t-value of exactly 0. We'll see that in the when we start looking at the equation, but a t-value is very close to a z-value. If the null hypothesis is true, you would expect to get a t-value close to 0. And you can see that down here in the curve. This is a t curve. It looks very much like a z curve. But if you get a sample mean close to 1875, then you're going to get a t-value close to 1875. Or excuse me, you're going to get a t-value close to 0. Basically, what the null hypothesis is saying is if there's no effect, you should get something close to a t-value of 0, and any deviation from that t-value is probably due to sampling error. Now, this null curve is, again, a distribution of sample means, and that means that anything in here is possible. But things close to 0, if the null is true, are very likely, because look how tall this curve is. This is a frequency curve, so t-values, if the null is true, that are close to 0 are very likely. Things that are far from 0 are unlikely to happen if the null hypothesis is true. Now, before we jump to the next stage, we need to talk about whether you should use a one- or two-tailed test. Now, there are some differences of opinion on this, but generally, well, always, a one-tailed p-value is going to be smaller than a two-tailed p-value. The two graphs will tell you the difference. So let's just say that we computed a t-value and it was 2.73. The one-tailed p-value is going to tell you the probability of getting a 2.73 t or something larger than that. And that is 0.006. That means that's only going to happen less than 1% of the time if the null is true. Now, if you're using a two-tailed test and you still computed a 2.73, that's the obtained t that you got, the two-tailed test is going to tell you the probability of getting something as far as 2.73 away on either end. So you would still have the 0.006 on the positive tail, but you're also going to add in the 0.006 on the negative tail and combine those to give you a two-tailed probability. Now, as a researcher, you want to probably get a small p-value because in most cases you want to find evidence for the effect that you're looking for. So there is an incentive for researchers to want to use a one-tailed test rather than a two-tailed test because it will find evidence for an effect more frequently. It'll give you a smaller p-value, and again, smaller p-values will make it more likely for you to find evidence against the null. Now, how should you choose? You shouldn't just choose a one-tailed test because you want to have stronger evidence. There should be a rationale for why you can use a one-tailed test. Unfortunately, in most situations, a two-tailed test is more appropriate. So how do you choose between a one-tailed and a two-tailed test? Some researchers make the decision based on whether or not they're making a prediction. Some statisticians are saying that that's the wrong way to make the choice. Rather than whether or not you're making a prediction, one direction or the other, the better way of making the choice is what you would do if you found something opposite to your predicted result. So here's an example using the overestimation study that we're looking at right now. If the prediction is correct and there is overestimation, what are you going to do? Well, you're probably going to write up the results and explain to people that there is this overestimation, and then possibly create an intervention to correct the overestimation. Maybe you create some kind of program explaining to students that there is this overestimation going on, and maybe recalibrating their expectations. So you would do something. You would report the results and then create an intervention. If your prediction is wrong, and it's the students are actually accurate in their estimates, you're probably going to do nothing because there's no problem. But you could be wrong in another way too. If your prediction is wrong and the students are actually underestimating their salaries, their starting salaries, what would you do? Well, if you would also report those results and then also create maybe a program and say, hey, you guys can expect more than what you're expecting. You might create another program. Notice that what you're doing in those two programs, or those two prediction outcomes that are wrong, differ. You're still going to do something if you find underestimation. These two outcomes, if they are different, the null result outcome and the one that's opposite of what you predicted, if you're still going to do something, if you get an opposite result, then you should probably use a two-tailed test. The only time a one-tailed test would be justified is if underestimation and an accurate estimation, if both of those you would do nothing. If you would do the exact same thing for a null result and the opposite result, that's when a one-tailed test would be justified. And in most situations, if you find something the exact opposite of what you really predicted, you're going to write about it. You're going to report it, and you're going to try and figure out why that happened, because if you could figure out why it happened, you would understand the phenomenon more effectively. So in most cases, a two-tailed test is the more appropriate test. The next step in hypothesis testing with a continuous p-value is to graph the data. Here you see a point and whisker plot where it's plotting the mean of the sample's wage estimate. Now, it's not telling you the exact value for the mean, but it is placing it on a number line here. And it's comparing that to the population's mean wage. So the actual population mean wage is $18.75. And here we can see that the sample is overestimating. We don't know exactly how much because we'd have to actually compute the mean, and we'll get that later, but it is overestimating. And these whiskers represent 95% confidence interval. And because the actual population wage is not bracketed by this 95% confidence interval, you can anticipate that you're going to get a pretty small p-value, that you are going to have compelling evidence against the null hypothesis. And you're probably going to conclude that there is evidence that the population of students in this case are overestimating their starting wage. The next step is to actually compute the single sample t and then determine the p-value. As you can see, the single sample t, you take the observed mean difference and divide by estimated sampling error. That's the mean that comes from the sample estimated wage, which is right here, $21.88. That's what they estimated. You want to find the difference between what they estimated and the true value of $18.75. And then you're going to divide that by sampling error, which is the standard deviation of the sample divided by the square root of the sample size, which was 25, which gives us 2.73. What that literally means is the deviation in the numerator is 2.73 times larger than you would expect by sampling error. Whenever you get that much more, when you get something that large, you know you're probably going to get a small p-value. So the next thing is to actually look up that p-value. Now, if you're doing this on a computer, the computer will automatically give you the p-value. If you're doing it by hand, you'll have to go look up the p-value in a calculator on the website. But in class, we'll mostly be doing this on a computer, so you won't need to do that. So here we find the p-value. Again, we got a p-value. It's a two-tailed p-value. So again, this is including both tails. So it's the probability of getting something 2.73 away on the positive side or on the negative side. Now we need to interpret this p-value. Technically, or literally, the p-value is the probability of getting the obtained t, which was 2.73, or something more extreme, either something on this tail or on this tail, further away than 2.73, if the null hypothesis is true and if there are no methodological flaws in the study. So again, if the null is true, we would expect to get a t-value somewhere in here, somewhere close to 0. But we didn't. We got something way out here. How likely is that to happen if the null hypothesis is true and students are actually accurate in estimating their starting salary? Well, that's this outcome. It could happen due to sampling error, but it's only going to happen with a p-value of 0.012. So it's going to happen about 1 time out of 100. It's going to happen very rarely. So this is very unlikely to happen due to sampling error. So this is fairly compelling evidence against the null hypothesis. These data suggest that the population of psych majors in this example overestimate their starting wages. Now we're going to move on to the next pillar of practical importance with effect size. You have a number of choices. You have 2 choices when it comes to computing effect size in this case. You can use the mean difference, or you can use something known as a standardized effect size, or Cohen-D. Let's talk about the mean difference. So in this case, it's simply the sample mean estimate, wage, that difference from the population mean. And that difference is $3.13 per hour. In most people's lives, if you were making $3 more an hour, that would have some practical implications on how you would conduct your life. So just by the mean difference is often a very useful way of thinking about the effect size. It's likely that a mean difference of $3 an hour, $3.13 an hour, is going to have practical importance for the population. So students are overestimating by that much. That's a pretty large effect. Another way of thinking about effect size is with a standardized effect size, or Cohen's d. And that's computed by the mean difference divided by the standard deviation, the sample standard deviation in this case. And when you do that, you get a 0.546. And generally speaking, when you interpret a d, a 0.2 is considered small, a 0.5 is considered medium, and a 0.8 is considered large. Now, the standardized effect size is useful because it allows you to compare studies, even though these different studies might use different scales. For example, if I wanted to compare this study to maybe a similar study that was done in China where they don't use dollars, I might compare the D computed from this study to the D computed in that study. So it would allow me to compare studies that use different DVs more easily. So both of these DVs are used, or effect sizes are useful. It's just a matter of which one is more useful for what you are trying to do. In this case, if I'm not trying to compare this result to another study's result, I might be tempted just to use the mean difference here because it's already in a frame of reference. All of us know what $3.13 per hour means. I mean, we can readily see the practical importance of that. And so if we're not really ready to compare our results to another study that uses a different DV, I would probably use this one. If we do want to compare our results to another study that's using a different DV, I would probably use this one. Now we're ready to move to the next pillar, and that is population estimation with confidence intervals. It's also useful to try to estimate what the population parameter might be, because as we know, the sample overestimated by $3.13. But that doesn't mean that the population does that, because the sample probably doesn't represent the population perfectly. Because of sampling error, the overestimation in the population could be considerably more than that, or it could be considerably less than that. And so what we do is we compute a 95% confidence interval. And we talked about this in the previous chapter. You take the point estimate of 313, and then you add to that and subtract from that the margin of error. The text talks about how you would actually compute this by numbers. I'm not going to go into that right now. If you're interested in that, go ahead and review the text again, or send me an email and we can talk about it, and I can send you an explanation. But mostly we'll be focusing on interpreting the confidence intervals this semester rather than computing them. So in this case, the mean difference, or the amount of overestimation, could be as high as the upper bound here of $5.50 per hour, or it could be as low as 76 cents an hour. All of those are plausible values for the overestimation that happens in the population. Now that's a pretty wide range, obviously, and so that means that if you want to have more precision in your estimation of the population parameter, you probably want to increase your sample size. However, when I interpret this interval, obviously an overestimation of $5.50 an hour is a huge effect. That would be, if that were going on, you would definitely want to try and correct that overestimation. But I would say even an overestimation of 76 cents is pretty sizable. If you multiply that times 40 hours a week, multiply that times 52 weeks a year, that over a year that you're going to be underestimating or overestimating your yearly salary a fair amount. So even the smallest plausible value has practical importance here. So that's something you want to focus on. If the smallest probable value, the lower bound, still surpasses what you think is practically important, that's something you want to talk about. You can also get a 95% confidence interval around D. Now, that is something that you would definitely use computer software to compute. We don't even explain how you would do that in the book, because you don't do that by hand. You would just use software to do that. In this case, the upper bound could be as high as 0.96, which is a very large effect. Again, over 0.8 is large, to as small as 0.12. And again, a small effect is 0.2. So again, this tells you that you have a very imprecise estimate of the population parameter here. The overestimation could be a very large effect, or it could be a very small effect. And again, that's just a fact that comes from the fact that the sample size was so small. When you have a sample size of just 25 and a lot of variability, you're going to have an estimate of population parameter that's very imprecise. When you have very imprecise estimates, it's good to be cautious when you interpret your results. Don't overstate them. Just say, well, gee, it might be a large effect, it might be a small effect. If we need more precision, we should probably have a bigger sample size. The last pillar is, of course, considering the research methodology that generated the results and then comparing your results to those reported in the literature. When you're evaluating the research methodology, you just want to ask yourself, were there any methodological problems? Were there anything that would lessen your confidence in the data? You also might consider whether there were weaknesses in the research design. Were there ways that it could be strengthened? We'll talk a little bit more about that stuff as we go through this semester. Finally, you also want to compare your results to those reported by other researchers. If your results are consistent with those reported by other researchers, that should strengthen your confidence. That should make you more confident in your results and their results, right? If you find results that are inconsistent, again, it doesn't mean that one or the other study is wrong and you pick and choose. Instead, what you do is you would carefully evaluate the two studies, compare the methodologies, compare the populations. Is there something different about the two studies that might help you explain why one found one outcome and another found a contradictory outcome? If you can identify and then explain why one study has a different outcome than the other, that's exactly what you're trying to do with science. You've understood the phenomena more deeply now. You are, and then explaining that to the literature, and you've enriched the literature with your contribution. So very often, an inconsistent result is really an opportunity to learn something new. Finally, you want to report your results, and you want to form them into a well-supported scientific conclusion. Every scientific conclusion in this class should have 6 things in it. You need to say what you compared and how you compared it. You need to report the statistical parameters, or the statistics, I should say, not statistical parameters, that doesn't make sense. You need to report the statistics in APA format. You need to interpret the p-value, interpret the effect size, interpret the confidence interval, and then you need to comment on the methodology and the literature to the extent that you are able to do so. So that is all done here, and hopefully I've tried to color code this to make it clear what you're doing. In the first sentence, I'm describing what was compared and how it was done. We computed a single sample t-test and effect size to compare the average expected hourly wage of psychology majors, and then I tell what it was, to the actual starting wage, and then I tell what it was. So again, I'm telling what I've compared. And then in the green, I'm providing the statistics in APA format. Here is the sample mean and standard deviation. Here is the fact that I ran a t-test with 24 degrees of freedom, the sample size -1, the obtained t-value, the p-value, the 95% confidence interval for the mean difference, the d, and then the 95% confidence interval for the d. This is just a transitional sentence. We interpret these results below. Now we need to interpret the p-value. Well, this p-value was quite small. It's very compelling evidence against the null. Again, if the null were true, we should get a t-value of 0 and a p-value close to 1. We got a p-value close to 0 now, so that's very compelling evidence against the null. These analyses suggest that psychology majors tend to overestimate their future starting salaries, and that their overestimation is unlikely to be due to sampling error. That's what this small p-value says. This mean difference is unlikely to be due to sampling error. Then we want to interpret the effect size. The sample of students overestimated average wages by $3.13 an hour, which is substantial and likely to have practical importance. Again, I chose to go with the dollar, the mean difference, rather than the D, because I thought it was more informative in this context. Then you want to interpret the confidence interval. The confidence interval suggests the range of plausible parameters is quite wide. Therefore, replicating the study with a larger sample size would yield a more precise estimate and the amount of overestimation that occurs in the population of psychology majors. So this is basically saying we need to be pretty tentative here because it's very wide. Then finally, you want to comment on the methodology and the literature. It's also a good idea to replicate the study of another university, because this was only taken from one university. So one limitation of the study is maybe this university is unique in some way, and we want to compare it to other universities. So again, replicate at other university because it's possible that these students do not represent all psychology majors. Overall, these results are consistent with the results of the optimism bias reported by other researchers, and I cite them. So again, this looks like a lot, but if you think about it in terms of these 6 things and try and come up with something to say about each of those things, you'll come up with good, well-supported scientific conclusions. If you're interested in learning more about statistics, visit us at learnstats.com.